Hello and welcome to the Data Engineering Podcast, the show about modern data management. What are the pieces of advice that you wish you had received early in your career of data engineering? If you hand a book to a new data engineer, what wisdom would you add to it? I'm working with O'Reilly on a project to collect the 97 things that every data engineer should know, and I need your help. Go to dataengineeringpodcast.com/97things to add your voice and share your hard-earned expertise. And when you're ready to build your next pipeline or want to test out the projects you hear about on the show, you'll need somewhere to deploy it, so check out our friends over at Linode. With their managed Kubernetes platform, it's now even easier to deploy and scale your workflows, or try out the latest Helm charts from tools like Pulsar, Pachyderm, and Dagster. With simple pricing, fast networking, object storage, and worldwide data centers, you've got everything you need to run a bulletproof data platform. Go to dataengineeringpodcast.com/Linode, that's Linode, today and get a $60 credit to try out a Kubernetes cluster of your own. And don't forget to thank them for their continued support of this show. You listen to this show to learn and stay up to date with what's happening in databases, streaming platforms, big data, and everything else you need to know about modern data management. For more opportunities to stay up to date, gain new skills, and learn from your peers, there are a growing number of virtual events that you can attend from the comfort and safety of your home. Go to dataengineeringpodcast.com/conferences to check out the upcoming events being offered by our partners and get registered today. Your host is Tobias Macey, and today I'm interviewing Michael Tegtmeier about Turbit, a machine learning-powered platform for performance monitoring of wind farms. So, Michael, can you start by introducing yourself?
Hi, yeah, of course. So, I'm Michael, and I'm the founder and CEO of Turbit Systems. And we are basically a data analytics platform for wind turbines. And we have built some tools to make the maintenance and operation of wind farms more efficient. And I'm looking forward to a great conversation.
And do you remember how you first got involved in the area of data management?
Yeah, of course. So my education is a physicist. So I somehow always was dealing with data in the university when we made some experiments, and then also you had to write some programs to analyze data, of course. So that's like one part where I got confronted with some data, let's say, and also maybe some super complicated data. And in my studies, I wrote my bachelor thesis about some measurements I did on wind turbines. So as you should know, wind turbines need to be directed into the wind in order to generate power. And what I was doing in that bachelor thesis was I was making measurements with a laser system. It's called LiDAR, so light detection and ranging. And with that laser system, you could see the wind direction and the wind speed in front of the turbine. So that means that the turbine could, or that was at that time, that was somehow the vision to control the turbine before the wind is actually at the turbine. So see what's coming in before the turbine, and then have some control algorithms that turn the turbine in the right direction and the pitch of the rotor blades in the right angles before the turbine actually, before the wind is actually at the turbine. So, but the measurement itself was like, of course, again, with a lot of data, and you had to match these data of this new LiDAR system with the data from the turbine, like when is the turbine running, what wind speeds were measured with the LiDAR system, what wind speeds were maybe measured with some other systems, like some anemometers on top of the turbine. And and so to make this story maybe up until I get to Turbit, later on, then I was still doing some physics. I also I made my master in laser physics, but this time in pulse shaping, temporal and space pulse shaping. And we did this with splitting a laser beam into its parts, into its different frequencies. And then you could control each frequency, the polarization and the amplitude of that frequency. And then you put the laser together, and then you could have a laser pulse that's formed in the time domain. So like there's coming a lot of energy in the beginning of the laser pulse, and then maybe later a little bit more. And what we were doing there is that we were trying to get electrons out of the atoms. And we didn't really know how to push the electron, to put it in some easier words maybe, So the electron is moving in the atom, and at some point in time, you need to push the electron out. So, and we didn't really know how to form that pulse. And we did this then with trial and error and basically with a genetic algorithm. And that was the first time where I have seen the power of such algorithms. And I got super interested in the power of what you could do with data analytics and let's say the first idea of machine learning. It's not really machine learning, but first algorithm that comes into searching how a computer is finding something out that you don't know about. And then later you try as a physicist to understand, okay, what was going on there? Why did it work? Why were we able to put the electron out of the atom just with this form of pulse? And that was quite interesting. And then later with my knowledge about wind energy, I was thinking like what to do, in life after studying. And I was looking for something that maybe is also it sounds maybe stupid, but making the world a little bit better. And I came to renewable energies, and I found wind energy most interesting because parts are turning. You have a lot of data. You have it's international. You can go around the world, and it has everything that you need for your brain to have some interesting things to work on. And that's how also I decided to found Turbit Systems, because actually this is quite a interesting story. Maybe the first time I got on the turbine was with this LiDAR measurements, and I got quite dizzy, like some sort of seasick. Like the turbine tower is like 100 meters high, and when you're at the top, and the turbine is switched off or is even running, there's a lot of movement of the tower, and if you cannot look outside because you are inside of the tower, you get seasick. And I was thinking, okay, if there's so much vibration due to the wind, then of course you need to see some wind direction also in the wind movement. And then together with some mates from the university, I was looking into that problem more deeply, and I found out, there is a relation between the wind direction and the type of the movement of the tower. And that also meant that you could maybe see the wind direction more precisely. And so we did some measurements, and this is how I came to found Turbit, actually. And then later we became more a data science company.
Yeah, it's definitely a very interesting problem domain because, as you said, wind energy is ubiquitous in terms of its availability around the world because the air is always moving. So it's something that can provide a lot of benefit, particularly for countries who are just starting to build out their renewable infrastructure. I know that Germany's been using wind energy fairly heavily for a number of years at this point, so I'm sure that also helped in terms of access to be able to build out your product while being able to sort of remain local and do things within your home country.
Yeah, totally. Like, apart from Denmark, I hope I'm not saying too much wrong here, but apart from Denmark, Germany has been quite early in wind energy. And of course, Germany is always known as a engineering country, maybe. And like wind energy has been here at my home. I'm born in Bremen, and we have a lot of wind turbines there, and also around Berlin, in Brandenburg, there are many, many turbines. And I could see that they exist, let's say. And of course, Germany is a good country to build a new company for wind energy, I think, because of all the resources that you have here and the knowledge and the connections that you can potentially get. On the other hand, also maybe Germany is very special in the wind energy domain because of its history. And that's actually a good thing. Wind turbines are owned in Germany by many, many people. There's like this thing which is called Bürgerwindenergie, so energy for the people, let's say. And then small cities, they invest with many people in a wind turbine, and then they profit from it financially. And this concept, maybe you don't see so much in other countries like the USA or China, where there's more like big manufacturers that own big wind farms. And yeah.
And so for Turbit Systems in particular, I know that one of the main focuses of the product that you're building out is to help improve the overall operating efficiency of the turbines, both individually and in aggregate. So I'm wondering if you can just talk a bit more about some of the ways that you're helping to optimize the output and some of the most problematic factors that contribute to performance degradation in wind turbines and in both individually and in aggregate.
Mm-hmm. Yeah. So basically, a wind turbine is like a plane. So it has wings, which we maybe call rotors, and they are directed, and they must be shaped in a very special way, and they must be directed into the wind while the turbine is turning in a very special way. We call that pitch, and then also the turbine rotor plane needs to be directed into the wind, so that actually the turbines are facing into the wind, which we call yaw. And both these pitch and yawing needs to be optimal in order to get all of the energy out of the wind. And so when I was talking about the LiDAR system in my bachelor thesis, the goal was to correct the way the turbine is turning into the wind. So the problem is that in big wind farms, you have other turbines in the wind park that are creating turbulences, and you have maybe sites or a forest at some sort of some part of the wind park that is redirecting the wind in a weird way, let's say, and you want to make sure that the turbine algorithm or the turbine behavior is always in such a way that it gets the maximum possible power output, so that it's directed correctly into the wind, and also with the pitch systems. So, but if you have a measurement of the wind on top of the nacelle that's behind the rotor plane, then you always have some errors, and you want to be able to correct this. And in addition to that, it's like a very simple problem that sometimes the technicians that go up and put the anemometer that's measuring the wind direction on top of the nacelle, they do this with an error, and sometimes with like more than 5 to 10 degrees, and nobody's detecting that. And then you have a bad performance of the turbine. So this is how we started with, as I said, with the vibration measurements. But then later on, going more in the data analytics part, where you get a lot of information from the turbine, or potentially get it. So the turbine is logging a lot of data, like wind speed, wind direction, temperature of the outside air, then temperatures of the gearbox, temperature, like a lot of data, up to 500 different values. And up to now, or maybe up to the past 2 years, nobody really analyzed these data, these huge data sets. So another thing that we found out is that sometimes the turbine is operating in a throttle mode that nobody knows about. So sometimes because of regulations, because of noise regulations, the turbine should not produce much power, or is producing less power than it actually could. And sometimes these turbines go into these noise modes without anybody knowing it. And so we figured out, okay, let's do some general analyzation of the normal behavior of a turbine, and let's look if there is something that we can find where the turbine is not behaving in a normal way. And that's totally a data analytics problem. We don't really maybe have all of the domain knowledge of one particular turbine, how it should turn and how it should behave, but we can look at the data and see and look for abnormalities. And with that example that I was talking about, you can understand, like, if the turbine is producing half the energy that it could, then of course this is a huge factor, an economic factor. And if you find these data points and these turbines that are not producing enough energy, then you clearly have a value that you can give to your customers.
And so you mentioned that at least up until the last couple of years, that a lot of this data that was being collected with the systems that are embedded into the turbines is being ignored or not analyzed in any great detail. I'm wondering what the current state of the art is as far as being able to analyze the performance of the turbines and correct for errors and do any sort of preventive maintenance to reduce downtime.
Yeah. So up to now, there's a standard, at least in Germany, to have 10-minute average values of different measurements at the turbine. For instance, wind speed, power output of the turbine. And so that's the standard. And basically, this data has been logged in the past just because of regulations. For instance, like if the turbine is shut down because of too much energy in the grid, then in this case, you have the data to see and look, okay, there has been such amount of wind before this event, and you would have generated so and so much energy because of this grid shutdown. And that's why basically maybe people were logging data. But now people also start understanding that you can do more with the data. So also more data is logged in newer turbines, and there are more sensors, and the sensors potentially can not only log 10-minute average values, but also maybe second values or sub-second values. So potentially you can get more data than you could get maybe in the past. And it's a physical system. The turbine is a machine, and you can grab a topic and look into detail and look at into the data and see if you can optimize something there. So just to give that example again, to where you can reduce the power, where the power of the turbine is reduced because of some regulations or because nobody's noticing it. Yeah, maybe I can explain a little bit more how we do it. So we basically try to find data sets that we definitely know about, that the turbine is behaving in a good way. So we filter out these data sets, and we call them our training data set. And then we train neural networks on this data set. And we have to think about, okay, what physical system makes sense? Like, what is the input of that black box formula, and what's the output? And the input for the power output can be, of course, the wind speed, but the energy that's contained in the wind is also dependent on the density of the air, and the density is dependent on the temperature, for instance. So if you have a value, a time series maybe of wind speed and temperatures of the outside air, then you can use these two values as an input to generate the power, to simulate the power output. And if you have a data set where you know, okay, the turbine is behaving correctly, then you can train a neural network on that behavior, and then you can simulate with new data sets how that turbine should have behaved in that scenario, in that physical scenario. And then you can make comparisons. You can add some more information like status logs and other ERP data and service data from the maintenance companies, and mix everything together and create a value out of that.
And then as far as the types of data that you're able to access from the sensors and the control systems in the turbine, what are some of the challenges that you're dealing with as far as just the data collection, and what is the level of variability between different turbines and different manufacturers, and being able to account for variability in the levels of accuracy or the representations of data as it's coming out of those control systems?
Yeah. For a good ride, there have been companies on the market that have had specialized exactly for that problem, because every turbine somehow is a prototype. Because if maybe let's say you buy a turbine from manufacturer A and you put it in your site, a specific site, and then you have an additional contract for data management with another company. And so you can imagine how many potential variations of combinations of manufacturers and data collecting computers there are on the market. And that means that there's a huge variety of the data sets. So we also had to learn that in the beginning. And you cannot assume that that if you have one turbine type, that the data is looking always the same, because you don't know if it's been generated by the same type of system. So the best way to deal with that problem is to look at each and every turbine as one system, and not make cross correlations too early with let's say if you have one turbine type and you want to make cross correlations with many other turbine types of the same model. So the same turbine type, and make cross correlations over that. You better set if you have, like, for each and every turbine a specific model, and that also means again that you have a lot of machine learning models, that you have a lot of data that you need to train. There's a lot of scalability problems, let's say, that you have to look to. And and then of course the standard data problems. You have data gaps. You have data points that are weird, like outside temperature of 1,000 degrees. So you need to handle that, or constant temperature of -10 during summer. Doesn't make sense also, degrees Celsius, of course. Yeah, and you need to clean your data set. I think every data scientist knows how problematic that can be. And so that's has really been a challenge to build some automated systems that clean these these data sets that are that have a great variety.
And then in terms of the actual collection of the data, how are you handling getting it from the turbines, and how much of the information are you processing or filtering on the collection point versus how much you're bringing back into your core service layer for being able to do more aggregate analysis across multiple turbines?
Yeah, I think in general, you can ask yourself as a data science company, if you delete data, you delete information. So if you say, okay, I don't trust this data point because it has 1,000 degrees Celsius outside air temperature, then you can ask yourself, okay, why is that so? Is it because of the real turbine control system, or maybe it's the sensor? Maybe it is a calculation error during data collection, and you want to know that because maybe that's the problem that the turbine has. Maybe it's the sensor. Maybe the temperature sensor gives you weird values, and because of that, the turbine is shutting down. So you need to be, with data cleaning, you need to be quite. That's a big point. If you want to throw away data, or so what we basically do, we mark data as not trustable, let's say, and then we can later reanalyze. Maybe that's because there's a sensor error, and so we basically get everything that we can get, and then later we flag data to be trustworthy or not. And so to answer your question, I think the most preparation of the data is been done on the database that we have.
Today's episode of the Data Engineering Podcast is sponsored by Datadog, a SaaS-based monitoring and analytics platform for cloud-scale infrastructure, applications, logs, and more. Datadog uses machine learning-based algorithms to detect errors and anomalies across your entire stack, which reduces the time it takes to detect and address outages and helps promote collaboration between data engineering, operations, and the rest of the company. Go to dataengineeringpodcast.com/Datadog today to start your free 14-day trial. And if you start a trial and install Datadog's agent, they'll send you a free t-shirt. And then as far as the overall system architecture of Turbit, how have you designed the overall pipeline of being able to go from collection of that remote data at each of the individual turbines into your central system for being able to then provide the dashboarding and analysis for your customers, and just the overall life cycle of data as it propagates from the control systems in the turbine through to the analysis that you're delivering to your customers?
Mm-hmm. So basically, we get the data in different time periods, sometimes in real time, sometimes every hour, sometimes every day. It depends on the customer and whatever the customer has set up in his turbine. And then this data is logged into the database or written into the database. And then we have different jobs running on the database, cleaning the data, flagging data. And we have jobs that train the models that then jobs that generate simulation data. Then we compare the data with so the simulated data with the real measured data. And then we can detect, we have jobs that detect abnormalities in this data sets. And then finally, one has to ask himself, okay, what is really the value to the customer? Is it detecting abnormalities or is it detecting an error? And what does it mean detecting an error? Like, in the best case, it is something like a real action point that you can give to your customer. For instance, okay, gearbox temperature has been too high for the past 2 months, so you better send up a service team to check why that is. Or maybe you can even tell the customer why the temperature is so high. And this last part, I think, is the most important part, because there you really need to understand your customers. You really need to understand what's the problem that you're really solving. And that's, I think, also as a data scientist, sometimes you need to maybe focus more on your customers than on what you generate as data sets. And yeah, you really need to understand what are you delivering to your customer.
And on that point too, how much of a feedback cycle are you able to build with the Turbit system as far as being able to determine some of these turbine misalignments? Are you able to then feed that back into the turbine itself to be able to automate some of that correction? Or does it require generating a notification to your customer who's managing the turbine and the wind farms to then be able to do their own maintenance or operations as far as bringing the turbines into alignment and things like that?
Yeah, so if you generate some action points for your customers, they basically get an email or a pop-up message in our web tool or in the app, and then they can understand, okay, I have something to solve here. Then they can put it in their own schedule and solve the problem. And after that, they can give us feedback. So there are some basic questions like how helpful has this been to you, or how relevant has this been to you, so that in the next iteration, we can then flag these detected events and understand, okay, if we show this kind of error, how relevant was it to the customer, or how good were we with a prediction, so that we can then improve the way how we do stuff, or use that labeled data to retrain other neural networks to do some optimizations.
And then the other question, too, as far as being able to build useful notifications, is having the necessary domain knowledge of how the turbines work and the atmospheric conditions that contribute to different performance outcomes. And I know that you mentioned that you have some background of doing research and working with turbines, but what are some of the other ways that you're incorporating some of that domain knowledge into your product to ensure that you're able to provide the most value to your customers?
Yeah, I think there are some things that you really need to know, that you have to learn also as a data scientist. Like, let's just give an example. Like, if you don't know that the turbine has a limited power output. So if there's a lot of wind, the turbine will never produce more power than, let's say, 3 megawatts. And it depends on the manufacturer and turbine type. And if you don't know that, then you might think, oh, maybe the turbine is not generating enough power. And this is like just an example of some domain knowledge that you need to know in order to train the networks correctly and to to make the right conclusions out of your data and data analytics. And then sometimes there's also stuff that or problems that you cannot really know if you don't have 20 years of experience as a turbine technician. And in these cases, we just have a network of other companies that we work with. And we can then give them that problem, and then they can analyze it. And together with our customers, they then can make the decisions what to do next with that kind of very special problem.
And then as far as the work that you're doing to build out this product, what are you finding to be some of the most challenging aspects of building an analytics solution for the wind energy sector?
I think handling so much different data sources was and is the biggest problem. And the second is the quality of your data. And you really want to make your you want to build a data lake and not a data sump. I don't know if that's a correct word, but you want to have a good data pool, and that's really hard with so many different data sources that you cannot really trust. And then maybe another thing is also making things scalable. Is a hard thing. You have different connections to many different turbines, and internet connections are breaking down very often, and this is like really a huge problem.
And are there any particular technologies that you've been able to lean on to help with some of that scalability problem in terms of being able to handle the data collection and ensure that you're able to get reliable throughput?
Yeah, we're working together with a company called Swarm 64, and they basically managed us to handle a lot of data in real time. And with real time, I really mean real time, like 1 second or sub-second values. And they help us to solve that scalability problem. If you get more data, and even so much data that you cannot handle it with usual databases any longer. And what we also want to achieve, we want to give feedback to the turbine in real time. And for instance, that could be that you have one turbine standing in front of the wind park, and it's getting a wind gust. And that gust is moving through the wind park. And then the first turbine is telling the other turbines, okay, there's coming a wind gust, and you should better behave like this or like that. And this information is then sent back to Turbit. The algorithms are giving the best way how to yaw and pitch the other turbines in the wind park. And all that is happening in real time. And for that, you really need to handle a lot of data very fast.
And for cases where you have maybe some sort of weather system coming through an area, are you then also able to feed that information to other installations of turbines that might be in the path of the weather event in terms of being able to improve their energy output, or maybe throttle them so that it prevents potential damage if there are especially high wind gusts or things like that?
Of course, like if there's a very momentarily wind gust coming to the wind park, you could potentially do that. If there's a huge weather system coming, that's mainly part that's mainly the job of the grid operators, mainly that, because they need to shut down some turbines in advance because they're knowing, okay, we are going to produce a lot of energy and that's too much for the grid. So let's better shut down some of the turbines. And that's actually happening quite often in Germany, especially in the north and at the seaside. There are some turbines that are shut off 50% of the time, and nobody's using the energy that the turbine could potentially generate during these times.
That's another interesting aspect to this system, is the energy storage and energy distribution capability. I'm wondering how that factors into some of the decision making that you provide to the turbine operators as far as ways to ensure that they aren't generating excess energy that's going to just get dumped, or generating excess energy that is going to potentially overload their grids or storage systems, and ways that you're able to maybe bring that information into the overall equation, or some of the other external data sources that you're able to rely on to feed into your models.
I mean, yeah, you're right. It's quite interesting, and there's tons of topics and problems that you could potentially solve. This particular problem that you're mentioning right now, we're not solving at the moment. As far as I know, there are other companies around that do that have specialized on predicting weather in the future and predicting the power output for the grid operators, and then you can trade day ahead auctions for electricity, and that's totally another problem that you want to solve there. And for us, it's more the operation of the turbine, and if you have the turbine running, let it run the best way it can. And I mean, yeah, I see a lot of potential in analyzing also that kind of data, and we also getting weather information data from a third party source, but this is more because we want to understand the operation of the turbine better and make the operation of the turbine and the service and maintenance better of that turbine.
And then as far as your overall experience of building out Turbit Systems, both from the technical and business aspects, what have you found to be some of the most interesting or unexpected or challenging lessons learned in the process?
Yeah, I think talking about what I said earlier, like the last question is, I think it's focus, especially when you're starting a company. It's quite hard to, also as a scientist, you have so many ideas and you know that so many things are potentially working out. But in order to bring something to the market, you really need to focus and you really need to understand what problem you are solving, and you need to concentrate on maybe one problem first and do that the best way you can. And then later on, you can add more problems that you solve. I think that was the biggest lesson of the past years. Yeah.
And as you look toward the near to medium term of what you're building out, both technically and in the business, what are some of the things that you have planned that you're most excited about, or overall trends in the energy sector or technology capabilities that you're looking forward to try and incorporate or take advantage of?
Yeah, I'm basically very excited about how much other problems there are in this data that you could potentially solve. And the more we are growing and we are able to handle and to manage all these different problems, the more I'm looking forward, because it's really fun. And basically this it's really the real time control algorithms for the turbine that fascinate me the most. And I think there's a great potential in the real-time operation of the turbines. But sometimes it's the basic things that give the most value, and it's sometimes technically not so fancy, but you're just solving a basic problem, and that has a great value for your customers. And sometimes that's the better things.
Well, for anybody who wants to get in touch with you or follow along with the work that you're doing, I'll have you add your preferred contact information to the show notes. And then as a final question, I would just like to get your perspective on what you see as being the biggest gap in the tooling or technology that's available for data management today.
I think the biggest gap is really the handling of how to clean the data. So you have great packages like, let's say, TensorFlow, with which you can train models easily, and you can do almost everything with that. But there's not, I don't know if it's possible, but there's nothing like a general solution for cleaning data sets. I would wish that there's some sort of a solution for that. And maybe it doesn't exist because it's too complicated, but I would be super happy if there's a package that does that for you.
Yeah, I'm sure that plenty of people would be happy to see that as well.
Yeah.
All right. Well, thank you very much for taking the time today to join me and discuss the work that you've been doing with Turbit Systems. It's definitely a very interesting problem domain and an interesting technical solution that you're building for it. So I appreciate all of the time and energy you've put into that, and I hope you enjoy the rest of your day.
Thank you very much. I enjoyed it.
Listening. Don't forget to check out our other show, podcast.init, at pythonpodcast.com to learn about the Python language, its community, and the innovative ways it is being used. And visit the site at dataengineeringpodcast.com to subscribe to the show, sign up for the mailing list, and read the show notes. If you've learned something or tried out a project from the show, then tell us about it. Email hosts at dataengineeringpodcast.com with your story. And to help other people find the show, please leave a review on iTunes and tell your friends and coworkers.